Hey guys, welcome to Safi Mixed. In this video, I will let you know about the concept of radian and will develop an empirical relation that links the arc length of a circle to its radius A, the central angle. To understand this, let us consider this figure in which I have attached three balls of different colors to a rod, and I want to rotate this rod about its one end counterclockwise like this. So the motion of these balls have followed a particular pattern. You may have noted it. However, if you haven't, let me visualize this further. You see, each ball follows a circular path of fixed radius. To see this once more, let me rotate it once again now in a more clear way. So every ball follows a circle of fixed radius. Now I want to describe this motion in terms of three different parameters. For this purpose, let me rotate the ball through some fixed angle. I represent the initial position of the balls by this dotted line and this final position by this dotted line. Now let us observe the arc lengths of the three balls. The arc length of the red ball I represent with S1 and the radius of the red circle I represent with R sub 1. Similarly, the arc length of the blue ball I represent with S2 and the corresponding radius of the circle with R2. And similarly, the arc length of the green ball I represent with S3 and the radius of that circle with R3. Let the central angle subtended by this motion between the initial and final positions be theta. Then from this geometry, we see that the lengths between the radii of the three circles is given by this one relation where R1 is less than R2, R2 is less than R3. And a similar relation exists between the arc lengths. That is, arc length S1 is smaller than S2 and S2 is smaller than S3. Now, there is an important link between the ratios of the arc lengths and the corresponding radii. That is, if I find S1 over R1, that is the ratio of the arc length of red circle to its radius, this is always equal to S2 divided by R2 and is always equal to S3 divided by R3. This important ratio is then equal exactly to the central angle subtended by this motion at the center of this concentric circle. Okay, in general, we describe this relation for any circle like this one where I have taken a single circle in the green color and I'm representing the arc length with S and the radius with R in the central angle theta. Then this relation for any circle is written in this form. That is, the ratio of the arc length S to the R at this position is exactly equal to the central angle. Now let us observe this equation. Since the angle is written as the ratio of two distances, the arc length is a distance and the radius is a distance, therefore the angle is a dimensionless quantity. That is, theta is purely a number, but for the sake of measuring other different physical quantities that can be expressed as the time rate of angle, we measure this in order to have an estimate of its quantity. And that measurement is carried in the following way. Now, if we choose the arc length is exactly equal to R, that is, this situation where the arc length is exactly equal to radius of the circle, then substituting this value into this one equation leads to theta equals 1. That is, the central angle would have a magnitude of equals 1. And when this is the situation, we call this quantity, this magnitude of the central angle equal to 1 radian. So 1 radian is the magnitude of a central angle subtended by an arc of length equal exactly to the radius of the circle. Let us see how many radian are there in one complete rotation of a body or a circle. For that, I redraw another circle of radius equal to r, and I divide the whole circle into a number of different arc length, where each arc length is equal to radius r of the circle. So if I do that, now this arc length is equal to this radius, therefore the central angle subtended at the center must be equal to 1 radian, and that's what I write over here. So this angle is 1 radian. Now I further rotate the ball over the same circle, and now this arc length is again equal to 1 radius, so I write that radius over here, and now the total central angle from the initial position equals 2 radian. Let me move the ball further over the circle and see what happens. This arc length is again equal to 1 radius, and I put that over here, that this is equal to 1 radius. Note that this orientation of the ball is not exactly opposite to this position. Rather, there is a little angle between the two positions. And now this whole angle from this position to the initial position is obviously equal to 3 radian. Let us move the ball further over the circle and see what happens. Now again, this is another arc of length equal to r. Therefore, this total angle would be equal to 4 radian, and I write that over there. Let us move it further over the circle and see what happens. You see, now this length is also, now this arc length is also equal to 1 radian. That's what I write over here. And this total angle from this position to the initial position equals 5 radian, because now we have 5 arcs, 1, 2, 3, 4, and this one is 5. If I further move this to 1 radius over the circle, then I have this total angle equal to 6 radian. And now this arc length is obviously less than 1 radius. That means there are 6 complete radian in a circle plus a fraction of a radian. Okay, now I want to create a link between this new measure of angle and the degree, which we already use as a measure of angle. And for that, I use our previous knowledge. We know that one complete rotation equals to circumference of a circle, and therefore I write for one rotation S, the arc length equals 2 pi r, that is the circumference of the circle. Now if I substitute this value in this equation, I can write theta equals 2 pi r divided by r, and the r cancels with r, leaving me with 2 pi radian. So the angle subtended in one complete rotation equals 2 pi radian. And we also know that one complete rotation equals 360 degrees. So that means 2 pi radians equals 360 degrees. And therefore I can write this thing, 2 pi radians equal 360 degree. So I can find 1 radian equals 360 degrees divided by 2 pi, and putting the value of pi, which is 3.16 or 22 divided by 7, I can set this equal to 57.29 degree. So 1 radian equals 57.29 degree. This means that degree is a smaller unit of central angle, whereas radian is a bigger unit. Thanks for watching.